Welcome. Today I'd like to talk about a project that I led that applied machine learning to some modern astronomical surveys. The purpose of the project was to to do science, to do some new astronomy. But the reason I want to describe it here is because I want to show you some skills that I developed in mastering some sophisticated machine learning and data manipulation that would be applicable over a much wider range of contexts than just astronomy. The layout here is I want to describe a bit of astronomy, just enough to kind of understand the next step, and then go into the machine learning and, well, first the data manipulation, then the machine learning. So, what you see across the image in the middle here is a survey taken by NASA's Spitzer Space Telescope. I was involved in this project. It took many years to take small images and then stitch them together across the central heart of our Milky Way galaxy. These images are in infrared light. It was the first time such a high resolution data set was collected. And when that was done, all sorts of new things were discovered. The thing I want to concentrate on today, I'm showing here in a kind of postage stamp insert into the lower resolution image, is this green shell shape. We called these wind-blown bubbles because our interpretation was that a hot star has pushed its surrounding gas away from it, and that creates this shell appearance when we look in the infrared light. So these shells were seen throughout the Milky Way galaxy. In total, about 3,600 were identified. However, they were identified literally by eye. We had a collection of professional and amateur astronomers looking at many, many, many images to identify those shapes. Some of them were as nicely identified as the shell that I just showed. Some were partial or more ambiguous. This was done enough years ago that machine learning and specifically image processing techniques weren't where they are today. My project today that I led and developed and that I want to explain to you is how we adapted modern convolutional neural networks to try to replace the role that humans did by eye. We began with the data set. So what you see here is a single image. It's an infrared light. And you can see a typical bubble that is this shell shape that you see at the center. Just so you can kind of see a more close-up vision, this is mostly but not exactly circular, and our goal is to identify those pixels that are inside the shell and versus those that are outside the shell. So we want to segment this image. That is, we want to do image segmentation, where each pixel gets assigned a 1 if it's inside and a 0 if it's outside the shell. However, I want to do one step better than what the humans did. Humans, when they did this, actually looked at 3 different infrared images. Excuse me. They looked at 3 different infrared images. They were colored red, green, and blue, but it was infrared data they were looking at. However, computers can look at a wider range of data without having the trouble of only having red, green, and blue cones in the retina of their eyes. So what I've done is designed a model that incorporates 6 different colors. So some of these are in the infrared, and you can see them labeled. But then the last one is radio light. So the reason for all of these different colors, especially the radio light, is that there's different physics behind each of these. That is, the mechanism that makes the different types of infrared light is different, just like red and green and blue light for what you see with your eyes, is produced by different things. Different things produce the different types of infrared or radio light. And so I want to construct a machine learning model that takes advantage of that information. So first off, all these data were not easily available. I had a catalog of where humans had identified those 6,000 or 3,600 bubbles. So I had positions and sizes, but I oftentimes had to go to the source of these surveys, which had images arranged in a different structure for each color. And so constructing that data and making it more regular is not something I'm going to go into detail here, aside from saying it wasn't a simple task. It involved data manipulation and data checking and data confirmation. That is, the sort of data structuring, the data mining that, yeah, it takes some effort. So just want to say that that was a process that took some time, and then and it's experience that I'm familiar with. So the goal was to design a model that would use modern machine learning. So for image analysis, I chose a convolutional neural network. Very briefly, the idea of a convolutional neural network is you have a matrix of numbers that is convolved with an image, and then an activation function is applied. And the goal of the numbers in the matrix is that when you space it around the image, it will pick up on structures. For example, the simplest structure might be a horizontal line. That somehow it produces ones every time that matrix passes by something that looks vertical. If you choose different numbers in the matrix, you can arrange it so that it only recognizes horizontal lines or diagonal lines. So we start with several filters and the training process is it choosing numbers to try to figure out what structures to look for. So I used a UNet style, which is a little more complicated, that does several layers of this with the goal of identifying complex structures in different parts of the image. I will not try to describe that in detail, but I would love to talk about it in an interview. I also applied these same matrices at different levels of resolution, which I'll talk more about in a moment, or later on in the discussion here. But the end result of bringing these 6 images in and applying this UNet-style convolutional neural network is, in the end, we end up with a single frame, a single image, that's the same resolution, 1024 by 1024. Each pixel in that image contains a number between 0 and 1 because I've applied a sigmoid activation function. And that 0 to 1 number is a probability that that pixel is inside a bubble. Usually we then force anything above 50%, we say that's inside a bubble, and below 50%, we say it's not in the bubble. Although if we want, you can look at the probabilities as well. So we trained, we found from the human identified bubble catalog, we chose some of the best bubbles to train on. And what you see as a result of that is shown here. The image data is shown on the left. So for example, bubble 800, you can see that's what we started with. This is just one frame, the 6 different colors which I showed earlier. And then the result, the trained model that was trained on this and other images or other sources, you can see here, and the grayscale is the probability. So in the center, it's well limited to being in the bubble. And then outside of that, you can see in the large frame, it's a bunch of black zeros indicating it's not in the bubble. So you can see something similar for bubble 805, which is 2 bubbles in the same frame, and bubble 821. However, that's of course all on trained data. So I'm showing you results of applying a good model that it was trained on. To get that result, I had to develop or adapt the several things that were unique to astronomy. And what I want to emphasize here is that I did not just take something off the shelf and apply it and it worked. This required deeply understanding how the UNet-style convolutional neural network works and designing my own pieces to it so that it would work more effectively for astronomy. The first I've already mentioned. The first adaptation was using 6 different colors instead of 3. And that's to allow a wider range of input information. Second, these satellite data are extremely high signal to noise. I mean, these are hundreds of millions of dollars to build these instruments and launch them and all that. And one result of all that money and effort is that the data are extremely high signal to noise. Something like 70,000 is typical. That is, the background is really, really low, and when we look at things, they can be quite bright and still well measure them. Unlike, say, your cell phone, or standard image processing, which has like a 256 or 512-bit PNG file. And so the signal to noise is much more limited. So in order to adapt for this, I needed to build, that is right, a computer program that did, it was a custom preprocessor and applied custom nonlinear scaling to account for this high signal to noise. I mentioned that I applied the convolutional matrices at different resolutions and then combined them together. The goal there was that bubbles, these wind-blown bubbles, if they are close by, they will appear large. If they are physically far from us, a bubble will appear smaller. But the matrix that we want to use to recognize that potentially is the same. And so we don't want to train on small objects and large objects as if they're physically different. So I applied the same matrix to different resolutions of the data, what it was equivalent to large close things or small distant things. And the reason to do that is because we want to limit how many free parameters we have. If you don't do this, you can end up with millions of free parameters and get very good fitting, but it's overfitting. And instead, I wanted to limit us to about 10 or 15,000 free parameters, that is, adjustable numbers, to much more strongly limit the fitting, that is, to try to prevent overfitting. We also had thousands of bubbles to fit on, with several surveys, terabytes of data, and a desktop computer to do this with extremely memory limited processing. So I could not load in all these data into memory at the same time. And it was all in an astronomy specific format, so I had to build a custom generator that would load in just the appropriate files and then do MIDI batching appropriately so that I wouldn't blow past any memory limitations my desktop computer had. And then the next adjustment I had to make was that if I just did the simplest image segmentation criteria, loss function and metric, it didn't work. And the reason is that many of these bubbles are quite small. Most of space isn't looking at a bubble. So like a typical image, say, would be 98% zeros. And in which case, a model would usually say, oh, it's all zeros, and it was 98% right, and it would have a hard time doing that useful thing of finding the other 2%. So instead, I had to adapt a custom loss function called dice loss, and the metric used was intersection over union, which I'd be happy to describe if you're interested in. But these are custom things that I had to write myself in order to account for the fact that many bubbles are quite small, but we care quite a bit about them. And then I had to adjust a learning rate to get ever smaller learning rates in order to get a better and better model. So what we see as a result of this, briefly, is on the bottom. You can see a plot. And what this shows is the intersection over union, where 1 is a perfect model, 0 is terrible. And the blue line represents the training data getting better and better as we repeatedly trained over several epochs, over the data set several times. And then the red or the orange line is the validation data. These are several bubbles I held to the side. I did not use, of course, the validation data for training, but every time I developed a new model, I applied it to the validation data to see what the intersection over union was. And what you see here is that the intersection over union got quite good over a handful of epochs for the validation data, but then there started to be a gap where the training set data is better than the validation data. And that's a warning sign that we have overfitting, that our model is learning things that are actually only specific for the training set and not more generalizable. So this is a complicated project. It's a hard project, honestly, and it's not complete. I wouldn't say that this model is done yet. So that's the limitation, but you can see, I hope, that by what I've done on this project, I have shown the ability to manipulate large data sets and bring them into a coherent whole that I can then feed into this model. I designed this model by adapting modern machine learning in a astronomy-specific way, and I was able to do the programming necessary to take advantage of things specific to astronomy. So the machine learning skills here are things that I could imagine applying in other contexts aside from astronomy, which I'd be happy to talk about should you ask. Why don't we stop there?